Okay, sorry. I can restart the computer. It seems. Okay, well, we have a good break. It's good to have fun, right? We're gonna have some more fun. Confounding. Because you confounded. What is confounding? We're going to talk about confounding. What is it? In a general sense, what is it? From a statistical point of view, it means what?
Two factors cannot be
You
separated.
can't separate them. You can't estimate them independently. Right. Okay. And usually in experiments, that's a problem because two different treatments might be confounded. You might can't separate the effect of the treatments, and that's what you're really interested in. You know, or you could have a block that's confounded with a treatment factor of some kind. You can't separate the effect of the block. Okay. So that confounding sounds like a bad thing, but in fact we can take advantage of it, and that's what we've been talking about. So the basic idea of confounded factorials is we can decide what effects we want to lose information on. Okay, we decide maybe some of the higher order interactions we want to lose some information on, and then we will say, okay, we're going to confound those effects with incomplete blocks. So we're going to lose some information on those higher order effects because we confound them with incomplete blocks. We ultimately can get information on them. But then this allows us to get more information on the main effects and lower order interactions. That is the idea. Okay, so last time we were talking about if I have a 2 to the n series and I have blocks per replicate of 2 to the m, then how many effects do I have to confound? Develop a confound factorial. Just trying to refresh your memory here. So I got, say, 2 to the 4. And I have 16 treatment combinations. And I have blocks of size 4, so that means I have 4 blocks per replicate, because I have 16 treatment combinations and I have 4 blocks. So that means 4 experimental units per block. So that means I have n is what in that case? If I have 4 blocks per replicate, n is 2, right? That's 4. Okay. So what is m? Why is m important here?
It's the number of incomplete confounding.
It's the effects we're going to confound. How many we're going to confound. So the defining contrast that we have to choose, we're going to have to choose m of them. Okay. So if I've got a 2 to the 4 in blocks of size 8, that means I just have 2 blocks per replicate, each of size 8, then I just need to confound one effect. But if I have a 2 to the 4, 16 treatment combinations, and 4 blocks per replicate, that means this m is equal to 2, and that means I'm going to have to confound 2 effects. Okay, now when this always happens when you have smaller and smaller blocks, and this is typical in science. We have more and more factors you want to evaluate, but you have smaller incomplete blocks. You have blocks that are smaller. Okay, so how do you deal with it? Well, you just confound a bunch of effects. Fine. We just go on our way. We showed how to identify these blocks, all right? Okay. But there's an additional problem with this. If you think you confound, so you choose 2 effects you're going to confound. The problem is there's another effect that's also confounded. Okay, and those are additional confounded effects. Right, so the additional confounded effects and it's not hard to show, it's 2 to the m minus 1 additionally confounded effects. You purposely choose these defining contrasts. But there's an interaction between these contrasts, and these are the ones that you get in return. Okay? So confounded factorials are complex because what's called generalized interaction. And so we identify these terms by using the generalized interaction. Okay, so for 2 to the n series, we have 2 to the m minus n minus 1. So if m is equal to 2, then we just have 1 additional effect. So 2 to the, that'd be 4 minus 3 is 1 additional effect. Okay? And so, okay, if I have a 3 to the n series, and say I have 3 to the m blocks per replicate. Same idea, I could use modular equations to identify these blocks as we talked about. Again, I have n defining contrast that I choose, but it even gets messier with the 3 to the n series. Okay, so the additional confounded effects is 3 to the m minus 2m minus 1 over 2. And so on, we can go down to the 5, or the p to the n. Okay, this is the p to the m. We have m, but then this in general is p. Assume this is prime, doesn't have to be. D to minus 1 to the n minus 1. The whole thing divided by p minus 1. Okay, so we talked about this last time. And I think I gave you a little simple example where we had a 2 to the 4th, and we had 2 defining contrasts. What were they? Let's use some blocks of size 2. So I have 16 treatment combinations, and I have, let's 2 to the n. It's 4 blocks per wrap. So I need 2 defining contrasts. And I define these, is the pick I did, that let's assume that A, B, C, and D, D are the 2 chosen defining contrasts. What's the generalized interaction? Somebody tell me this. I just multiply, right? Okay, so if I multiply, that's what an interaction is. I multiply. And actually, physically, in your X matrix, you just multiply columns. That's where it comes from. So I'm just going to, actually, each one of these is a column in your X matrix. I just multiply, get another column. Okay? So I do that, what do I get? A, B squared, C, D. Is that right? Well, it's right, but this is a 2 to the n series. We've got to reduce it. How do we reduce that?
P1, P2.
What do we do with this? It's 0, because we have to use mod notation, right? So this goes to 0. The 2 mod 2 is 0, and so the generalized interaction then is A, C, D. So we know that we're going to confound 3 effects with incomplete blocks. We have 3 degrees of freedom among those 4 blocks in a replicate. There's 3 degrees of freedom. We know that there's 2 degrees of freedom, one each that estimates these. The resulting other degree, 3rd degree of freedom, is exactly generalized interaction. Okay. Okay, so this is the generalized interaction rule. Just kind of review what we did last time. So let's look at the questions on this. Yeah.
For the P2N series, the formula for additional confounding effect is the P to the N of P to the N.
It's P to the N, or M, right, sorry, that's right, P to the M. Very good, thank you. Yeah, it's just the same as what I have here. And then this should be, P, yeah, this should be P minus 1 to the M. Right, minus 1, that's right. Sorry. Good, other questions? We talked about it, yeah.
Now, what if the factors have different levels?
It's not, the same idea holds. There's going to be interactions that are confounded also, but it's not so easy to get what those terms are. Okay. You have a homework assignment, we have to ponder that, don't you? Okay. So hopefully you're thinking about that one. With everything I've talked about in this class at this point, you should be able to do number 3. Okay, number 1 and number 3. Number 2, hopefully you understand how to do this now, and I'll tell you. Okay. Other questions? Okay, let's look at a 3 to the n series. Okay, 3 to the n. Now it's a little bit, some complications arise. As if this is already not complicated enough. To understand these complications, first let's see how the ANOVA breaks out. To see these complications, let's look at the ANOVA. Okay, well, just let's say a 3 to the, let's say a 3 squared. What do we get for a 3 squared? Let's break out the treatment structure. We'll have 2 degrees of freedom for A, 2 degrees of freedom for B, and in the AB interaction, how many total degrees of freedom? That's going to be 4, right? But we need to break this up. We can break this up into AB1, which is 2 degrees of freedom, and AB2 with 2 degrees of freedom. Now, how do I get, now each one of these, I have to have a column in the X matrix for this, or actually 2 columns in the X matrix for A, for B, 2 columns for AB1, and 2 columns for AB2. So I need to be able to choose these columns somehow. How do I get these terms? How do I get that term? How do I use that? Let's assume I'm going to confound. How would I use that to confound? What do I do with this? I can use the exponents to get what? Mod equations, right? So I'd have to define an equation. Use mod, in this case 3, of L, which is going to be, in this case, 1 times Z1 plus 1 times Z2. Okay, we can use those to define, to identify these effects, to get the effects for the columns of the X matrix, right? We're using mod equations to get these. So this notation I'm using to break out these 4 degrees of freedom, I'm just using the same notation I did before with mod equations. Okay, everybody see that? Now, one of the things curious, look, I just have A just has 1, and there's no A with a 2 exponent. Okay, but I get my degrees of freedom and add up to 4. Okay, so that's the 8 degrees of freedom. Let's do a 3 cubed. What's that going to look like? Well, it's going to be A, which is 2, B, which is 2, AB, which is, we could break this as 4. It's going to be AB1, just as I did, AB2, which is just what I did. Then I can have AC, which is 4, and I can break this out to AC1, which is 2, AC2, which is 2. Then I can have BC, same idea. Okay, this will be 4. Again, it'll break out into 2. The same idea. This is just going to be B, C1, B, C2, right? And then the last term out here is going to be A, B, C, which is going to be 8. And now how many terms are there? Going to be 8 of them. So it's going to be A, B1, C1, which is 2. A, B1, C2, which is 2. A, B2, C1, which is 2. A, B2, C2, which is 2. That adds up to the 8. So if I think about all the terms that I'm breaking out by using my confounding motto notation over here, I can break out all these effects. I can put them into my X matrix to estimate them. I can also use those mod equations to identify my treatment combination. Right? In fact, I gave you some SAS and R code the other day to identify these treatment combinations for your blocks, right? And it's just using mod arithmetic.
Is there a reason you don't have C by itself?
Oh, C should be here too, right. So C is 2, sorry. Right. Okay, so I'm just breaking out all my degrees of freedom. The point is that, look, I take any interaction and it's broken up into these components. Right? Now, you got to be, look, each one of the leading components of every term has to have an exponent of 1. Of course, those do, of course. Nah. Okay, so by convention, or for uniqueness. So, for uniqueness. For uniqueness, the first letter of any component must have exponent 1. Must have exponent 1. And if it doesn't, then we have to square the term repeatedly and reduce it mod 3 to give an equivalent for don't. If it doesn't, if it does not, then repeated squaring of the term and reducing mod 3 will give an equivalent term that has a leading component of 1. Will give an equivalent component. Equivalent QUI. An equivalent component. An equivalent component with the leading factor 1. So, for example, I decide that I want to, in my analysis, I end up with a term that looks like this. A squared so you have to see what I mean here. Let me give you an example. So for example, I got a term A squared B1 C2. Problem is, the leading component has an exponent, not 1. So what I do with that? I square it. I square the whole term. So A squared B1 C squared, and I square that. That's an equivalent component. I square that, what does that give me? A squared B squared, or I'm sorry, A to the 4th, B squared C to the 4th, right? Now I reduce this mod 3, what is this? What's that term, mod 3? Well, no, the exponent. What's that term, mod 3?
1.
1. It's just a remainder, right? So what is this? This is A to the 1. B, we have to reduce that with B2. C to the 1. What is that? That's exactly A, B squared, C1. So I start with this term over here. Now, which one is it? It has to be one of these because I broke them all out. There they all are. It's got to be one of them. Which one is it? Which one? It's A1, B2, C1. That one right there, right? They're the same. Okay. You say, well, why do I have to go through this complication? Because you've got to be able to understand what your interaction terms are. That's the complication of confounded factorials. You have to understand and use these higher level ones, what the interaction terms are that you're confounding. Okay, in other words, we have to be able to get generalized interactions. So the question is on the specific technique here. Okay, so we need to use this to get generalized interaction. So this means generalized interaction for the 3 to the n and the p to the n series. It's a little bit more complicated. Okay, not only do we have to break out the ANOVA a little bit different, we got to make sure that leading term has always exponent of 1. There's a different rule for getting generalized interactions. Okay. So for any two components, x and y, the generalized interaction is obtained as the follows. It's very similar to what we've done, and just multiply and reduce, but then I have to have this complication in. So for 3 to the n, if I want the interaction between two components, x, y, what do I have to do? I just take the interaction between x raised to the 1, and then I have to add the interaction between x raised to the 2. So if I want to generalize interaction between any two of these components that I come up with, so I choose that one and that one as defining contrast, then I need to get their interactions, right? Okay, and so this is how you get it. Okay, if it's a p to the n series, then look. If it's a p to the n, then if I have two terms that I want their interaction, it's going to be x, y to the 1, plus x, y to the 2, all the way out to xy to the p minus 1. So it's complicated to get all these extra interaction terms. With the 2 to the n series, what you see is what you get. You only have that first one with the 2 to the n. Go 3 to the n, you get these extra terms out here, those generalized interaction terms. Okay, so let me give you an example. Let's see, this is a 3 cubed, so it's 27 treatment combinations in 9 blocks per rack. With 9, which of course is 3 squared blocks per rack. How many terms do I have to explicitly confound? What's n?
2.
N is equal to 2, right? Because I got to confound. Choose 2 terms to confound, right? Now all I'm going to do is I'm going to confound, let's say a, b, c, and a, b squared c. So a, b, just a, b was just this would be 1 here. Okay, I'm going to confound both these terms. Okay, but now I have to get the interaction. Okay, so I got to get the interaction between these two. So now to get the generalized interaction, I use my rule. It's AB1 times AB2C. And now I just multiply. So it's AB1 times ABC, or AB2C plus AB1, and then that whole thing has to be squared, times AB2C. It's equal to 1, actually. Be explicit. Put 1 on that. Now let's carry these out. And actually, this one is going to be 1 interaction term, and this will be the other interaction term. There's going to be 2 additional terms that will come out of this. Okay? So let's carry this out. So if I multiply these, it's just going to be a squared b to 3, right? And c, just c by itself. C is 1, right? Now I've got to reduce my mod by mod. What's this term reduced to? I use mod notation on these. So what's 2 mod 3? 2. What's 3 mod 3? 3 mod 3 is 0, right? Because you take 3 and divide by 3, the remainder is 0. It's just the remainder. So that's 0. So that thing turns into 0. So that thing goes out. So this is equal to what? A squared C1. Right? But it violates our rule. What does our rule say? We have to have that term as the leading one to be 2, or to be 1, right? So what I have to do with that term? I square it. Now if I square it, what do I get? If I take that term and square it, what do I get now? I get a to the 4th, right? C squared. Now reduce that mod 3, what do I have? A, just a 1, right? So I don't even need the 1 because it's a leading term. A to the 1, C squared. So that's 1 term. Everybody see what I'm doing? It's not hard once you see how to do it. It just takes a little time. Let's do this one. This is a little harder. This has to be squared here. Sorry. But let's square it first. So you have to do all your multiplications before you reduce it. So let's square it first. So this would be times a squared b to the 4th c squared, right? Now we've got to multiply those. Multiply before you reduce them. Okay. And this is going to be a cubed b to the 5th c squared, right? Okay. Now reduce them. What do we get? What do we reduce this now? 3 mod 3 is what? 0. So that just goes away. So 5 mod 3 is what? 2. So, just remainder 2. 2 mod 3 is just 2. So what do you end up with? You end up with b squared c squared, right? Okay, now let's reduce, we gotta get our leading x. What do? Is square that, right? Now I square it, what do I get? If I square that, that's gonna be b to the fourth c to the fourth. What's b to the fourth? It's just gonna be b because reduce mod 3, so this is gonna be b c to the 1. Okay. So these are the two interaction terms. So if I choose, I got a 3 cubed, 27 treatment combinations in boxes size 3. Okay. In boxes size 3, 9 blocks per rep. I have to choose 2 dividing contrast. Fine, we get the treatment combinations just as I showed you how to do it. The problem is you better pay attention to what the generalized interactions are. Now, I'll say to you, I'll ask you, the whole idea of compound factorials is usually we want to get most information on the main effects and the lower interactions as possible. Is this a good design? What's your choice as a designer of an experiment? Your choice is to decide which of these effects you're going to compound, right? Mother Nature gives us the blocks of size 3. Okay? It's our choice to decide how we're going to treat them, those blocks of size 3. So we can choose these, right? So, okay, assume that I chose those. So my question to you is this a good design? And that's the type of question I ask you on the test, right? Which is coming, we'll talk about that at least a week, right? 2 weeks probably. Is that a good design? Jamie, what do you think?
No,
Why not?
because both levels of C are confounded.
Sorry?
So like both levels, so C is in both of the confounded effects, like both levels of C are.
Well, that's true, but no main effect is confounded anywhere, right? There's no main effect confounded, so in that sense, it's good. What about two-way interactions? Well, why? How many two-way interactions are confounded with the design? If I don't want to confound any two-way interactions, this is not a good design, right? Because I got two-way interaction confounded here, I got two-way interaction confounded here, and a two-way interaction confounded there. So it's not a very good design. Okay? But the problem with these higher order designs, like a 3 to the n and so on series, is that often it's really hard to get a design where all the interactions, or all the lower interactions are unconfounded. Usually you're going to have to get confounding of some of the interactions, but hopefully not the main effects. Okay, everybody see the idea here?
So the main point is to not confound main effects.
First, yeah, that's homework assignment 3. First of all, number 1, don't confound any main effects. Right. Number 2, I think you want to have estimate two-way interactions with nitrogen or something with most precision as possible, and you have to have 12 degrees of freedom for air. Right. There's a list of things that you want to try to accomplish. Right. That's the idea. We don't want main effects to be confounded with incomplete blocks. Then we're in a split plot. Right. That's what split plot does. We don't want to do split plot. But the whole point of this is that we can do something beyond split plots. Okay. Other questions? With this. Okay, so you say, has anybody ever used this? Nobody ever uses this garbage, right? I ain't never going to use this. These statisticians just get too mathematical, right? Waste of time. Not true. An example of this. And you should be thinking about this, depending on your situation. If you've got a factorial experiment of some kind, and your units the blocks are small, if you have a number of factors, you should consider this seriously. You really should. Okay, here's an example. I got 3 blocks, or 3 squared, in blocks of size 3. Blocks of size 3. And what does that mean? That means 3 blocks per rep, right? 3 blocks per rep. What's n? This is easy, right? N is equal to 1. Well, let's assume the one I have. The example is in the greenhouse problem in plant pack. Okay, they're testing dry bean plants. Some of you know in Nebraska that dry bean production in Nebraska is probably number 2 in the United States. Huge amount of money in dry beans in the United States. Okay, and so we got 3 isolates of fungus. We're studying white mold. White mold is a fungal disease of beans. And actually, it's really a growing problem in soybeans right now. I got 3 isolates of fungus. And let's call this factor A. And I've got 3 substrates that I'm growing the fungus on. You know, to culture this fungus, you have to have them growing in some sort of soil or vermiculite or something. You got to have a culture of the fungus growing. You got to grow the thing so you use them, right? Okay, so how do you grow them? Well, you want to know how the different isolates. The isolates come usually from a leaf. You choose a leaf and you culture it up, right? So I got 3 different places where isolates of the fungus, and I'm growing it on 3 different substrates. Okay, 3 different media. Okay, so I got, and this is my factor B. Okay, and I got 6 pots here. 3 blocks of size 3, 3 blocks per rep, and I got 2 reps. And what are my reps here? I've got 6 pots of trifoliates. Here's my trifoliates. 1, 2, 3. There's the first rep. Okay, 4, 5, and 6. There they are, little plants in the greenhouse. And one of my experimental units are what? They're going to be the leaves. Okay, what I'm going to do, what do we do with this stuff is you take a little plug of the fungus and you put it on the leaf. Okay, you put it on the leaf and you come back in 48 hours. I put it in this chamber usually, but you come back in 48 hours and you see how big some people in here probably do. Are there any flat path people in here? I can't remember, but. So I put a little piece of isolate that's grown on a particular substrate here. I put it there and then I measure how big the area is after 48 hours. And that's my response. Well, look, what are my natural blocks? This is a block, right? The leaves are the experimental units. I got 3 experimental units per block, but I have 9 treatments. Right? Perfect opportunity to use a confounded factorial. Right? Well, a lot of people say, well, I'll do a split plot here. I'm going to do a split plot. It's easy. Okay, I can say I'm not so interested in substrates, so I'll have substrate 1, substrate 2, substrate 3, and then have the isolates of the split plot. Well, okay, you could do that. But you're not so interested probably in the interaction between these. You're more interested in the main effect of isolate. And so or substrate and isolate. And so you should try to confound the interaction with the incomplete blocks, or in this case, the pots. Okay, okay, so you see the idea? Now, your job, if you're going to use a confounded factorial, is to find the treatment combinations. How do I find the treatment combinations? I have to have how many defining contrasts? 1. Okay? I don't want to choose a defining contrast as the main effect, right? Because I lose the interaction of lose the information of the main effect. I want to confound the interaction. Okay? And so what let's do is let's confound AB2. Okay? So I can confound AB2. But look, I lose all the information on AB2 with those pots that I'm confounded with. But let's say I got a replicate here. Here's a replicate. I can confound AB2 with pots in rep 1. Then what? I can take the other rep, this is a rep 2 here, and confound another interaction. So at least I get some information on all the interaction parts. Okay, so I can confound AB1 with rep 1, and let's assume that I'm going to confound AB1 with rep 2. So for this first rep, I'm going to confound the interaction AB2 with blocks. And the second rep, I'm going to confound AB1. Now you can do that. Okay, you can do it by hand using your mod equation just to figure this stuff out. But I gave you the code. It's a little easier to do the code, right? Okay. So I'll just give you what the treatment combinations are. But if you want to test that you understand this, then you should make sure that you can do it yourself without having to rely on the computer code. Okay. So for rep 1, so I got AB1 is AB2 is confounded. What I get for pot 1 is 0, 0, 1, 1, 2, 2. This is pot 1 now. Pot 1 or block 1. Block 1 equals pot 1. And then, remember in complete replicate, we got all treatment combinations there. Well, there's the ones that are saying we can basically just rotate this. O2, 1, O, and 2, 1. And then the last one is O1, 1, 2, and 2, 0. And that's with AB confounded with this. Okay? Okay, we can just look at it. If I take my mod equations and take those numbers and plug them in, so the exponent's going to be 2 on the b's. So 1 plus 2 times 1 is 3. That'll be 0. Some of those is 0. And this would be 2 plus 4 is 6. Some of these are all zeros. These should be all the 1. So these are 0 mod 3 for the mod equation. These are 1. This should be 1 mod 3 for the mod equation. And these should be 2 mod 3 for the mod equations. You should be able to prove that. Okay. Now for rep 2, let's see, I'm going to confound AB1. And rep 2 will look like this. A, B, 0, 0, 1, 2, 2, 1. AB, 0, 1, 1, 0, 2, 2. And AB, the last one, is going to be 0, 2, 1, 1, 2, 0. Here the mod equation, let's say L1 is 1 times Z1 plus 2 times Z2. Where do these come from? That's a 1, right? 1 times Z1, 2 times Z2, right? Remember the mod equations. What is the mod equation for this one? L2. Now I got to reduce these mod 3, right? I got to reduce these mod 3. So L2 is going to be 1 times Z1 plus 1 times Z2. Reduce it mod 3. Okay? You can almost puzzle these out yourself without using mod equations at all, but it gets harder. You know, everybody see what I'm doing? I'm confounding information on the interactions with the pots, okay, or with the blocks to gain information. To gain information on the main effects. What's the ANOVA look like? Good question. What's the ANOVA look like? How many total observations are going to have? I take a measurement on each one of these. This is leaf 1, leaf 2, and leaf 3, right? Leaf 1, 2, and 3 for each pot. So how many measurements are we going to have? I'll take the size. So this leaf has the 0 isolate and 0 substrate. This leaf has isolate 1 and substrate 1 and so on. And I take a mean of these. I put the plug on there and then measure how big the lesion is, and I get, in this case, I'll get 18 observations, right? Okay. So what's the ANOVA look like? Source of variation, I get 17 corrected. Well, I certainly could have rep, which is 1 degree of freedom. Then I could put in the confounded effects. The problem is that it's partially confounded. I can't put in what's confounded effects are. It depends on what rep it is. So what I'm going to do is just ignore that. Let's just say block within rep. And how many blocks are there in each rep? There's 2 degrees of freedom among the blocks in each rep. So it's 2, then it's going to be 4. That's 5. Does that make sense? 5. Why is that 5?
6, 3 by 2.
Yeah, you got 6 pots, right? Okay, so this is the pot variation. Okay, there's 5 degrees of freedom among the 6 pots. Right, so that's pot variation. Now we have no confounding with the A effect. That's going to be 2 degrees of freedom. We don't have any confounding with the B effect. That's 2 degrees of freedom without any question. Okay. But the AB1, how much information do we have for the AB1 effect? This is also 2 degrees of freedom. Okay, there's going to be 2 columns in your X matrix for that term right there. You get it right out of your mod equation. 2 degrees of freedom, but there's a problem with this one. Why? What's the problem with this? Remember I put a little prime on it. What's the problem with this term? Well, it's not really a problem. It's not as good as these. Why? Yeah, it's part of it's confounded. So it's confounded. It does not come from rep 2. It cannot come from rep 2 because it's confounded with blocks. So I've already removed the effect of blocks up here. So I can't get any information on this from rep 2. It comes from variation from rep 1. Only from rep 1. Right? Only from rep 1. So variation only from rep 1. Okay, what about the other one? The same thing. 2 prime. This comes from only from block 2. Or not block, I'm sorry, rep. Only from rep 1 for that one, and only from rep 2 for this. Right? And error, well, by subtraction, you can just get it, but we can figure out what it is. I won't do that. It just should be 4. That's what I have here. Okay, notice this adds up to the what? The AB degrees of freedom. There's 4 degrees of freedom. So I got 2 degrees of freedom for A, 2 degrees of freedom for B, 4 degrees of freedom for AB, and then my error should be 4. Now I just use least squares on this. Simple least squares. You can calculate this with Excel if you want. Or if you want to be fancy, well, I use an X model. Use Glimix, you know. Use AIC and all that. Okay, but just we can calculate as random. Okay. As long as we adhere to this structure, we can use a generalized model. Okay. As long as we adhere to the structure that I'm talking about here in terms of confounding. Okay, are there questions on this? Well, I did one. We did one last year. Angela Bastidas did one, and I'll just tell you maybe about it. Maybe some of you people are doing similar kinds of things. Another example is she had, let's see, she had 5, stages of corn. So this is 1, 2, 3, 4, 5. Usually stage corn might count the number of leaves. And she had 5 cover crops. Okay, cover crops 1 to 5. I can't remember what they were. And she wanted to know if planting these cover crops into the corn, when the corn was at different heights, had an effect on the corn yield. Okay. She's got 25. This is a 5 squared, isn't it? Her blocks, this is so 25 treatment combinations. So she had to have 25 plots. I think I was telling you, each plot she had is about almost as big as this room. Okay, now you put 25 of those together in a block. That's a huge, huge block. That's going to violate the idea that you want your blocks to be as uniform as possible. Okay, and so what she did is she used let's see, 5 blocks per replicate in a confounded factorial. How many effects did she have to confound? She came up after class one day we did this. How many effects did she have to confound? 5 blocks per rep. Remember our little rule over here. A 2 to the end, a 3 to the end, a 5 to the end. Okay, so the number of blocks per rep was what? 2 to the m, right? How many blocks per rep? But what's m? She confounded one effect. That's all. These things are not hard. M is equal to 1. I can't remember which one it was. Okay. Now her ANOVA, what's the overall ANOVA? Well, then she had 4. She had 4 replicates. She had 4 replicates. But if you look at her ANOVA, I can't remember exactly which one she confounded. She had 4 degrees of freedom, for A, she had 4 degrees of freedom for B, and then you break out the interaction, so there's 16. You got A, B, 1, which is going to be 4, A, B, 2, which is 4, A, B, 3, which is 4, and A, B, 4, which is 4. So we had to choose one of these. I can't remember which one it was. Choose one of these and confound it. That's all you have to do. There's no generalized interaction there. You know what you're doing. It's almost the same as this. This is easy. Now, she didn't do partial confounding. She probably should have. I don't think she partially confounded it. Because she had 4 locations. Everybody see what I'm doing here? She had 4 locations. She should have partially confounded each one of these with incomplete blocks in each of her locations. Right? I don't think she did that. But maybe she did. I can't remember. You calculated precision on this experiment compared to doing it as a full randomized complete block design. She doubled the precision by doing this. She doubled the power. If you double the precision, you double the power. So these big agronomic experiments can have big time payoff. Okay? And you can do it. Everybody see the idea here? Okay. So I just encourage you to think about using these things. They're not there on you. They look kind of daunting at first. I mean, when we first started talking about confounding, people just kind of break out into a sweat. But once you see the ideas, they're not that hard. All right? And if you have problems like this, I'd be glad to help you try to conduct experiments with these kinds of things. Okay, so that's about all I'm going to say about confounded factorials. Let's wrap it up a little bit and talk about some of the advantages and disadvantages.
Just ask you something.
Sure.
Move on. So, if you, like in her case, if she was working, if she had no reason to believe that her block, if she used RCBD and had no reason to believe that blocks would be heterogeneous, then, I mean, did she have a reason to believe they were not homogeneous here, or what was the?
Well, I mean, if you've been working, it's out here at the Havelock Agronomy Farm, and they know how big of, people have got a lot of data on that. They just knew that those are big blocks, and they knew there's going to be a lot of heterogeneity in there. It turned out there really was. Now, did anybody ever do an experiment like this to figure out what the heterogeneity was? No, that's an added advantage of the experiment. We can actually estimate that, right?
But so, like, if you were to use past data to decide on this, and people have done, let's say, RCBDs there, could you look at that, go back and see if
Absolutely.
the block effect was significant, and then decide to do this?
Yeah.
Or?
Yeah, that's one of the things I'm going to say about the disadvantages. Let's write this up, and I'll try to build off of that. Advantages and disadvantages. One of the disadvantages, exactly what you say, is if, let's talk, I want to talk about the disadvantage in a second, but is if your blocks are complete replicates are homogeneous, what have you done to yourself? Lord, now all of a sudden you have to explain to your committee, because none of them know what compound factorial is. You have to explain to all your readers what this stuff is, okay? For what? You did not have increased any power at all. You better make sure that you're getting an additional, what's the scientific payoff here? Power. You better make sure you have enough power to pick up differences, increase the power on this to make it worthwhile. Now, if it's just for demonstrational purposes, I think it's probably worthwhile doing it without having to worry about that. But from a practical point of view, make sure your blocks are heterogeneous before you do this. The blocks are all equal. Okay. It's a good point, though. Okay? Okay, so I think that's the main downside of these things. Make sure the power is enough. And I'll write that up in a minute. What's the advantage? What's the main advantage? Main advantage. Just as I said, you can increase the precision way a lot, okay? Can be used to gain more precision. Can be used to gain more precision. Certainly compared to an RCDD for sure, right? Okay. How about compared to split plot? Get more precision on split plot with what? Compared to split plot, the traditional split plot. What would have Angela done in her problem? She's got these huge reps, okay, and she can break those up into little incomplete blocks, whatever they were, and she had 5 of them. So this is 1 rep. So she had 1 rep, and she had these 5 incomplete blocks. Okay, 1, 2, down to 5. She could run this as a split plot, couldn't she? She should just say, okay, this is all going to be corn at stage 1. This is all going to be corn at stage 2. That's all going to be corn at stage 2. But right? But the problem is the stage of the corn is going to be confounded with incomplete blocks. Well, that's stage. That's a main effect. That's what she's most interested in. How stage affected development of the plants in terms when you got a cover crop in there. Okay? So she could have done this as a split plot easily. Okay? But compared to split plot, what's the advantage?
Don't confound the main effect.
We don't compound any main effect. What does that do? We get within block information on all main effects. Okay? Can get within block information on all main effects, ideally. Okay? Whereas an RC split plot, what does it look like? A split plot, you got rep, you got factor A, you got rep by A, you got factor B, A-B interaction, and air, right? That's what a standard split plot would look like. In Angela's case, A would be, say, growth stage, and B is a cover crop, and so she could run this as a split plot. But for a confound factorial, what did she do? For a confound factorial, she'd have rep, and then she had part of the interaction, whatever it was, A, B, say 4, and then rep by A, B, 4, and then she had A, and she had B, and then the rest of the interactions, right? And so what does she have? She has the main effect, all the main effects in the split plot. Up here, the main effect's in the whole plot. We lose the information on the main effect because we had to put in the whole plot here. Okay. So this is another way to look at it. But by and large, just getting people to use incomplete blocking is a huge gain right there. But lots of times people say, recognize there's a problem in RCBD, so they do it as a split plot. You don't even do it as a split plot. You do it as a confound factorial. So these are the advantages, is what I would say. So what's the disadvantage? Like Leo said, the main issue is exactly that. Disadvantages. So confound factorial are not more precise. If confounded factorial not more precise than a RCDD, you're wasting your time, right? It's not worth it, okay? Much wasted effort. You're wasting your time. You're wasting time and effort. Why is the time and effort here? First of all, the effort to understand what these are and how to apply them. Then how to put them in the field. Okay, you got to be careful about that. How do you put them in the field? When you get the data, it's more complicated in terms of analyzing it. But that's what PhD scientists are for, right? That's what you guys are here for. You with these complicated problems. Why? To improve your power. Okay, okay, you wasted time and effort. Okay, so I would say it's not more precise than you are wasting time and effort. Don't use them, okay? How do we know? Well, what we can do, a simple thing, for example, so a rule of thumb, calculate the efficiency value. Now, this is a rough efficiency value. I'll just say equals at this point, but we could take the air sums of squares of an RCVD over the air sums of squares of the confounded factorial. Now, this is the final air. This would be the split plot air, basically. Okay. And so, well, if I want to make sure the confounded factorial is worthwhile, do I want this EFF value to be large or small? I want this to be large or small to prove that the confounded factorial is worthwhile.
Small.
Well, you mean I want air sums of squares for RCVD to be smaller than the air sums of squares? It's a ratio now. I want this thing to be large, right? I want to show that the air from the confounded factorial is half the size of the air from the RCVD. So I want this thing to be large. So rule of thumb, if the efficiency of this factor is greater than 1.2, then it's worth running. Okay, in other words, you get at least 20% improvement in precision. Okay, now you can analyze these. You can get that air sums of squares from RCVD really easily. Just don't analyze it with the incomplete blocks of the analysis. Right, the block within rep part, just take that out and model. Run it, you can get the air sums of squares. Okay. So if the air sums of squares is greater than 1.2, then our confounded factorial is worthwhile. So confounded factorial is worthwhile. Right? At least you're getting at least a 20% increase in precision if this happens. You're reducing the air compared to what would have been the randomized complete block design. Right? Now, there is an adjustment factor. I'll just say no, and I'll give this to you. No, must use an adjustment factor on EF. Must use an adjustment factor on EFF for small designs. And what do I mean by that? I don't know. The degrees of freedom for these two things. Degrees of freedom are, say, less than 10. This is for the RCVD air. And degrees of freedom for the confounded factorial. Say they're less than 10. Most of you people have more degrees of freedom than 10 air degrees of freedom. But, you know, if they're small designs, you need to be careful about this. So you need to adjust it. And so I give you adjustment factors. I'll give that to you later. Okay. So not only, if the confounded factorial is not more precise, you're wasting your time. Not only that, even if it is more precise, what are some of the other disadvantages? What are some of the other disadvantages of this? Even if it is more precise, even if the confounded factorial is more precise, what are still the problems?
Interacts.
Yeah, it's much more complicated. You've got to deal with generalized interactions if they exist. The analysis is more complicated. If you're talking about partial confounding, you've got to worry about that. You know, so the design and analysis is much more complicated. Complex than standard designs. Frankly, I don't think they're any more complicated than the split plots. Everybody loves split plots. If they love split plots, why don't we do confounded factorials more often? Okay. That's all I'm going to say about confounded factorial. So the questions on any of this?
Can you just repeat again that the adjustment factor you talked about? I didn't look at it.
Oh, well, it's a little formula. If you want me to give it to you, I can give it to you. It's, you take the adjustment factor, you take degrees of freedom for 1 plus 1 times the degrees of freedom for 2 plus the 3 over the degrees of freedom for 2 plus 1 over the degrees of freedom for 1 plus 3. And you take your EFF times that. And then use this. So this is your adjustment factor. And DF1 is, DF1 would be this. And DF2 is this. I'll talk more about this when we get to incomplete blocks. But you just have to multiply it by, if degrees of freedom are small, then this thing is not necessarily close to 1. If that's close to 1, who cares? Right? So it's kind of a detail. Okay, other questions? Please try to think about using it. Not too hard. The most important thing about this class is try to remember these things. You know, 5 years from now, I mean, it's so easy to forget this. You know, just try to put in the back of your mind somewhere. Oh, there's some ideas that came out of that class, and you know, usually when you do anything for people, you know, you think, I hope that in 6 months they can remember one thing that I said. One thing in 6 months. Or in 5 years. Of course, I've been pounding on you for how long now. So. Anyway. Okay. Now, so we talked about general linear models type background for the data analysis methods we use. We spent a lot of time talking about split plots. Now we talked quite a bit about confounded factorials. Now I'd like to start talking about incomplete block designs. Now we've been talking about incomplete block design. The idea here is there's more treatments than the number of experimental units per block. Well, that's always the case. Think of Angela's problem. The incomplete blocks, say these are incomplete now. The incomplete blocks are size 5. She has 25 treatment combinations. Right? Okay, so the confound factorial is an incomplete block. If you think, so I'd say no. Confound factorials are incomplete block designs. They're using factorial. Also, I'll go so far to say that split plot designs are incomplete block designs. I want somebody to tell me why that's the case. Why are split plots incomplete block designs? Here's my whole plot factor. Okay. I got 5, in Angela's case, I've got 5 different stages of corn development. 1, 2, 3, 4, 5. And I'm going to apply those to a group of 5 plots. And then within these, I'm going to randomly assign my 5 treatments in there, right? We say that's a split plot. Everybody understand, this is main effect A, so 1, 2, 3, 4, 5 is applied to the whole. And these are the split plot levels, B. 1, 2, 3, 4, 5, right? Why is that an incomplete block?
Then have one of each day represented in each block.
How many units do we have here? That's what you're saying, right? 5. How many treatment combinations do we have? 25. Say I got 5 levels of A, 5 levels of B. I got 25 treatment combinations. I only have 5 units in the whole plot. So what are the incomplete blocks when you think about split plot design? They're the whole plot units. Okay, so the whole plot units are the incomplete blocks. So we've been dealing with split plots inside of the incomplete block design. The whole plot units are the incomplete blocks. So what's different? What am I going to be talking about here? If this is all, we're going to talk about new incomplete blocks. Oh Lord, are we done with it? We need to get on somewhere interesting. I'll walk field or something. No. Well, right, we've been studying incomplete blocks for almost this whole class. But what is different about the ones I'm going to talk about? No, on both of these, for both the confounded factorials and the split plot designs, there is an ordering of importance in terms of the effects. There is an ordering of importance of the factorial effects. For the confounded factorial, normally the mains are the most important, right? So we're using the idea. The confounded factorial, we want to confound the interaction with the whole plots. The main effects are more important. What about the split plot design? What's more important? The interactions are more important. So what we're doing here, the interactions are more important. Right? Fine. These are all factorial effects. What do I do if I don't have any factors? Like all primary students in here, right? For scientists. Is you have one factor. You have stream. You have line, whatever it is. You have one factor. There's no factorial structure. You don't know what to do. You don't know what you don't have any main effects. You don't have any interactions. You have one factor. That's it. Basically one factor. So what to do when there is no ordering of importance? When there's no ordering of importance of effects. These are the incomplete block designs I'm talking about. These are the standard designs. These types of designs are called incomplete block designs. Where there's no factors that help you establish the ordering of importance. That is, there's no factors to help decide the order of importance. Everybody see the idea? So, what do we do when there's no ordering? When there is no ordering. What to do when there's no ordering of importance of effects? These are the types of designs called incomplete blocks. We got to have something that's important, right? Something's got to be important. So the kinds of incomplete block designs that people talk with these, same idea, you got blocks that are too small to hold all treatments. What's the defining principle behind incomplete block designs? Anybody know? Here, the defining principle is what? All statistics could be thought of as an optimization process. If you're not doing some sort of optimization process, you're not doing statistics. okay? Statistics is a discipline, okay?
If you're analyzing your data, fine, but analyze your data using a method that you're trying to optimize something.
Here, the defining principle of these kind of design is to what?
To minimize the variance of a difference between two treatment needs.
That's all. So we got two treatments. We want to minimize the variance. So how many pairs? There's lots of different pairs you could look like. We want to choose the design that minimizes the variance of that difference. Why is this so important to us? Because we're talking about comparative experiments here in this class. Comparative experiment is an experiment where you compare, you're only interested in comparing treatments. You don't want to predict anything. You just want to compare one treatment with another. And so we're talking about confounded factorials. Well, essentially we're doing this, but we have some sort of a structure in terms of the treatments. If we don't have any structure, we don't know how to order what things are most important. The defining principle is this. We want to choose the design to minimize the variance of a treatment difference. Okay.
And so that's kind of where we're headed here, is we talk about these kinds of designs.
Now, I'll give you the easiest one you possibly have. Somebody know what the easiest incomplete block design like this is? Easiest possible incomplete block design. Even your Uncle Bob will understand this. What's Uncle Bob? I have an uncle that's always saying, he's still alive, he's 95, still doing well, you know. He's, what are you doing? Now I have start time to understand what I'm doing, you know. We should be able to explain these ideas, right? Somebody give me the easiest incomplete block design you could possibly have. 3 treatments, 3 blocks. Okay, here's my block. 1, this is number of units per block. 2. Block 1, 2, and 3. So there's the blocks. 2 units per block. So I got 2 units per block. Here they are. What treatments did I put in the first one? Or I got to put 2 of the 3. 1, 2. What did I put in the second one? 1, 3. 2, 3. Right? That's the simplest possible incomplete block design that you could have. Turns out, it's perfect. It's interesting. Okay? Why is it perfect? Because it minimizes these. All of them minimize the smallest possible difference between treatments that you can possibly make using our standard statistical model. Okay? And that's called balance. What's balance? It's the number of times that each treatment is with each other treatment in a block. 1 is with 2 exactly once. 1 is with 3 exactly once. 2 is with 3 exactly once. This is called a balanced incomplete block design. And I'll stop here. And we'll continue talking about incomplete block designs next time. Okay, you have a homework assignment due. I have a handout. I'm sorry. Somebody give me a handout over there. And here's a handout that will help you. I was going to go over it, or you can pick it up when you read it. But I did talk about this, and this should help you with data analysis. I've got SAS code in here, and I've also got R code. So you should be able to do section. You should be able to do all of it. And so I'll see you next time.